So we've been really emphasizing what, like for type 2, for instance, left to right, and then bottom to top. But for at least one of them, they actually, the way the integral is set up, it has the correct functions, but it's actually right to left, and then bottom to top. So you'll know it's correct by the actual functions themselves that define the region, but it won't be what you're used to. So it'll be the bottom integral will be the right side, the bottom limit will be the right side, and the top limit will be the left side, for example. And so then, just like in a normal single integral, doing that, reversing the limits, will simply give you the opposite of your answer, right? So. And so that still applies for double integrals. So you just have to be on the lookout for it. That the limits are correct, but it's actually set up as going right to left instead of left to right. And that will simply just make the integral the opposite value, just like it did for single integrals. Okay, does that make sense? Any questions about that? Okay, so let's talk about, so we've talked about how we've talked about the meanings of double integrals. What did we say? So what does a double integral compute? What did we say it computes?
Net volume.
Net
The
volume,
sum
right?
of volumes.
Difference of volumes, right?
Difference of volumes.
Difference
Yeah,
of volumes, net volume, right? Okay. So here's kind of here's our general region called that D. Here's our function. And so remember that the double integral computes the sine volume of the solid formed, what? By F, between F and the xy plane, within the vertical cylinder defined by D's boundary, right? So either the top or bottom will be the surface and the xy plane, depending on where the surface is, right? The surface could be below or above, but it'll always be the solid between the surface and the xy plane, and then defined laterally by the boundary, by the perimeter of our region, right? So that's what we get. So we want to kind of talk about how we can kind of do something different with this. But in general, that's what we get. A double integral gives us net volume, difference of volumes. All the volume above the xy plane minus all the volume below the xy plane. All right, so what if the function was a constant function? Then what would the double integral give us? The double integral would give us like the volume of an actual like cylinder now, right? This is the volume of a right cylinder if that z was a constant value. And what is the volume of a right cylinder? Well, that's the area of the base times the height. And what would the height be then? The height would be k, or the absolute value of k, right? If k was negative, so it would be the area of d times k. Because now your height is the same everywhere. It's the value of the surface. So we can use this fact here to kind of trick our double integral, or force our double integral to give us the area of D. What could we do so that the value of the double integral then would give us the area of D? If for z equals k, we get the volume of the right cylinder of area of D times k, then how can we make this double integral give us area of D?
You could divide it by a constant z value.
Yeah.
No, I just want the double integral to truly give me the area of D. So I want the double integral to equal the area of D. So what would be required for that to happen?
Phase 1.
Yeah, right? So do you see that if k was 1, then do you see the double integral would be the area of D? So if I take a constant surface at height 1, right, then the double integral will be the area of D times 1, which is the area of D. So that volume, so I'm tricking it, the double integral, into giving me a volume that's the same as the area of the base. See that? So if k equals 1, that would mean that my function, right? So I want to take my function, my z value, to be 1. And when I do that, if I take the height or the function to be 1, then it's the double integral just of dA, and then that gives me the area of D. Now the units of it will still be volume units. It'll still be actually finding like a volume of a right cylinder with height 1, but then the value is the same as the area of the base, or the area of the region in the xy plane. Does this make sense? So in general, the double integral gives us net volume. It gives us change in volume. But by making the function 1, the volume that we get is the same as the area of the region, or the area of the base of that solid. So in a way, we can kind of trick a double integral into finding area for us, finding area in R2. Okay, does that make sense? That's an important concept. Okay, so let's look at another double integral example, like the ones we were doing last week. This last one here. So here's a new one. And so let's set this up. So first of all, is this type 1 or type 2?
Type 2.
She wants type 2. Left to right, so it's going to be left to right. So what part of the region is 1/2 y and the square root function? This would be what part of the region?
Left and right.
Yeah, this would be the left boundary, right? Because dx means go left to right.
Yes, sir.
And then bottom to
Top to
top.
bottom, or bottom to top.
Bottom to top. So one thing that you may have noticed, I didn't point it out, but you may have noticed that your outside integral is always going to end up being constants. So that's a good thing to remember, that it's just always going to be the starting value of that variable to the final value of that variable, kind of the strips that we make here. So we kind of make strips in the inner integral, and then we take those strips from some constant to another constant. And that's always going to be the case. You can't have any variables in your limits on the outside integral. Okay, so the left is 1/2 y. So x equals 1/2 y is the same as y equals 2x. So something like this. And then the right, does anyone recognize what that is? X equals square root of 25 minus y squared.
Isn't that an equation of a circle?
Yep, square both sides and move the y squared over. You got x squared plus y squared equals 25. So that's our circle with radius 5. Okay, and so if this is the left, so the bottom is 0. And so before we investigate the top, let's find the intersection here. The intersection of y equals 2x and this. So if x equals square root of 25 minus y squared, we also know that x is, at that point, x is also 1/2 y. So if you do the math, you will indeed, we're not going to take the time to do the math, but you're going to square both sides. No, we can do 1/4 y squared equals 25 minus y squared. So you get 5/4 y squared is 25. And then you get y squared equals, 5/4
20, I believe.
20. Thank you, 20. So then y is the square root of 2 radical 5. Right? That's square root of 20 is 2 radical 5. And then x is going to be half as much as that. Right? X is half as much as that. So this point is radical 5, 2 radical 5. So now let's look at our top and bottom. Our bottom is 0, y equals 0. Top is 2 radical 5. So lo and behold, the top of this thing is actually that point right there. It didn't have to be. It could have been down here, but it ended up being right there at that point. So there we got it. We got left from left to right, bottom to top. So here's our region right here. So it's like a piece of pie. Questions on that? So now what do we want to do? We want to change this into the other order. And we're going to use our sketch to do that. We're not going to try to do that by looking at these limits. We're going to look at our sketch, like we said last time. So when we look at our sketch then, we've got what type? dy dx is type 1. So we're going to do type 1. Type 1 means bottom to top. So bottom to top, we've got to make sure when we look at this, is the bottom all one piece? Is the top all one piece? So how about the bottom of this region? Is it all one piece?
0.
0, right?
Yes.
It's all one
Bottom
piece and it's 0.
piece.
What about the top? Is it all one piece or is it split up?
The top is split up.
Yep, fire your arrows from below. They always pierce in at 0, but they pierce out or they leave this region in 2 different places. According to the breaking point is radical 5. So when x is less than radical 5, the arrows leave this part of the top. When x is greater than radical 5, the arrows leave the circle. So we need to split it up. So it's the bottom is always 0, but sometimes the top is y equals 2x. Sometimes the top is y equals square root 25 minus x squared. So when is the top 2x? When is the top 2x? When x goes from?
From 0 all the way to radical 5.
Need to leave. And then when is the top the circle? When?
Radical 5 to 5.
Radical 5 to 5. So we got it. Questions?
Wait, is that square root 25 minus x squared? Is that right?
Yeah, so if x equals the square root of 25 minus y squared, if you square both sides and then solve for y and then take the square root, you actually get the exact same thing like this.
All right.
Yep.
For sure.
Yep. Yeah, because the circle is x squared plus y squared equals 25.
I trust you.
Yeah. So in that way you can see that if you solve for x or solve for y, you'll get the exact same thing in both cases. All right. Any other questions about this one? So what if I wanted to compute the area of this pie piece? What would I do to compute if I wanted this double integral to, rather than compute a difference of volumes, I wanted to actually get this area? What would I do?
Would we set our... I lost my train of thought. We'd have to set something to 1, though.
Right, so we want to find a volume whose value is the same as this area of this region. So it's the same thing we talked about before. What surface will give me a volume from this double integral that's the same as the area of this base? What surface?
1.
1. Z equals 1, right? Or f of xy equals 1. if I do z equals 1, so here's my region. If I do z equals 1, or the function being 1, then the volume of that right cylinder will have the same value as the area of the base because the height is 1. Does it make sense? Okay, so we have it as a type 2 and we have it as a type 1. So so what about this? There's another way we can do this one. If we look at what we have here, we've got a circle starting here at the x-axis to some kind of radial line here at y equals 2x. Anything from Calc 2 ring a bell with that?
Coordinate.
What'd you say, John?
We can also solve this problem by using polar.
Yeah, so exactly. So polar coordinates would be an alternate way to do this. What are polar coordinates? What are the two coordinates?
Would it be cosine of theta and sine of theta?
No, just the coordinates in polar themselves. So
Is it the angle and the radius?
yeah, theta and r, right? So theta is like how far you sweep from the positive x-axis. It's your standard trig angle. And then r is your distance from the pole. So like this point right here, if this angle was theta, and then this distance from the origin or from the pole is r, then the coordinates of that point would be r theta. So theta is our standard trig angle. R is your distance from the origin. This should be familiar from Calc 2. And so if you see this region, look, it starts at some constant. It starts at a constant theta. It ends at a constant theta, and then the boundary here is a constant r. Distance, the circle is a constant distance of 5 away from the origin. So it's very well suited to polar coordinates. Okay, but we have some groundwork to do first before we can actually set this up. So we have to ask the question: what is dA in polar coordinates? So in rectangular, it's very easy. Everything is rectangles, so it's just length times width, right? dA is just a little rectangle. dx times dy, and that's for both type 1 and type 2. But in polar coordinates, theta is not a distance quantity, right? It's an angle measure. It's not a distance from one point to another. So dA is not as straightforward. So we have to kind of derive that, see what dA is. Okay, and so questions on either this example, changing it from type 2 to type 1, or this intro to polar coordinates?
Yeah, why couldn't we just integrate that plane z equals 1? Why are we setting up polar? That seems like it'd be an easier way to do it with the double integral.
So that's two different issues, right? So what function you could have any function in any coordinate system in terms of your surface. Polar versus rectangular is just a whole nother way to set up double integrals. So there's not a connection between there's not a connection between the fact that we chose z equals 1 to find the area and polar coordinates. It kind of sounded like you were trying to make a connection there. That's two separate things. Does that make sense?
Makes sense.
Yeah. So yeah, in polar coordinates, the same thing will apply. If we make the height of the function 1, we'll still get the area of the base. So it's two separate things. Okay, so here we go. So double integrals in polar coordinates. So here's kind of a general view of a region in polar coordinates. You have a starting angle, they're calling it alpha, and a finishing angle beta. And then you have some inner function, some radius as a function of theta, and then some outer function, another function where the radius is a function of theta. So with polar, so we're going to think about the inside function to outside function, starting theta to final theta. So it's like inside to outside. So this is like the cheer for polar, right? The cheer for polar is like inside to outside or inner to outer, and then starting theta counterclockwise to final theta. So inner to outer, sweep counterclockwise from starting theta to final theta. All right, so there it is, inside to outside, theta 1 to theta 2. So the order is, that order would be dr d theta, and so we won't be working with switching the order. So for polar integrals, it'll always be dr d theta. We won't have the situation where find it in the other order like we do with rectangular. Okay, so the order is d theta, but what is dA? So let's set it up here. If I take a little d theta, would be a little sliver of opening, and then dr would be a little change in radius. Okay, and so we're still going to have kind of rectangular-ish elements, but they're not based on x and y anymore, right? So they're based on distance, dr, and d theta, but theta is not a distance, right? So it's kind of a little weird. So here's our dA. So this dimension right here is our change in r. That's dr. So that's fine. That's a distance. But what we need now is we need this distance, okay, which is not d theta. It's based on d theta. So d theta is like the openness of the angle, but d theta down here is the same as, this is all d theta, and clearly that's a much shorter distance than this out here. So, and it's all d theta, right? That's all d theta no matter how far away you are. So what is the distance across this way?
Arc length.
It's arc length, right? So if you remember arc length of a circle, do you remember what the arc length of a circle was? Say this is alpha, and this is your radius. Arc length of the circle is not alpha, but alpha times r. So depending on how far you are away, the farther you are away, the longer that arc gets. And so r times alpha gives you the arc length. Therefore, if we're a distance of r away here, if our dA is r away from the pole, then what is this dimension right here? Based on what we just said.
Is it r d theta?
Yeah, r d theta. Right now the angle's d theta. So, and it's a distance r away. So now that's going to give me a distance unit. So what is dA? dA is length. So it's still going to be like rectangular. When things get really small, these curves kind of go away, right? So if it's super small, then this distance becomes a small little straight line distance. And we got r d theta times dr. And we said that dr comes first, right? dr d theta. So here's our dA. So it's almost dr d theta, but we need that extra r in there times the d theta to get that as an actual length dimension, so that it's like length times width of the little rectangle. Okay, so another question is, if we have an xy point, so right here, so this point right here, if the coordinates of that point are xy, what would they be in polar coordinates? So what would my x coordinate, if this is, say, this is theta, and this is r, then what are the coordinates of that point, x and y, in polar coordinates? So look, we've got our hypotenuse is r. So x is this what adjacent leg, right? This adjacent leg is our x-coordinate. So what would it be in terms of r and theta?
Our cosine theta?
Our cosine theta.
Cosine. R sine.
And then the y-coordinate is y sine theta. R sine theta, right? So that's, you should remember, that should be familiar from trig, right? From trig. So when we're transforming a function or an integral from, like, say, rectangular coordinates into polar coordinates, first of all, dA is not just dr d theta, but r times dr d theta, first of all. And then every x is going to be r cosine theta, right? Because it's going to be like the adjacent side of a triangle whose hypotenuse is r. And then every y coordinate will be r sine theta. So that's how we can make the transition, say, from rectangular coordinates into polar coordinates. dA is r dr d theta, x is r cosine theta, y is r sine theta. Okay, so let's write out kind of the general polar double integral then. So if I have an integral over a region, and it's in rectangular coordinates, whether that's type 1 or type 2, so this could be dx dy or dy dx. In polar coordinates, same region, but now every x is r cosine theta, every y is r sine theta, and our dA is r dr d theta. And so then we're going to integrate what? Inside to outside, theta 1 to theta 2, swept counterclockwise. Now, what about the r? What happens to the r? Well, everything is multiplied, right? You have the function multiplied by r, multiplied by dr, multiplied by d theta. So what happens to the r? It comes to the party with dA, but it goes home with f. Okay, so it links up, it multiplies with whatever function we have, and then becomes part of the integrand. So when we're doing the actual antiderivative with respect to r, this r is multiplied into this function first, and then this is the function that we're finding the antiderivative of with respect to r. F times r. The r coming from the dA. Does it make sense? Okay, so one thing is practicing. So let's go back to the example, and let's set up the example that we did in polar coordinates. Any questions on the kind of the foundation of polar coordinates? How we got dA was r dr d theta. X is r cosine theta, y is r sine theta.
Yeah, so when you're looking at the area down in the left corner there of dA, I just don't really understand why it can't just be d theta dr, because that would just make a rectangle, right?
Yeah, but look at here. This is state d theta, but this is just as valid as d theta up here.
Oh, I see. So
it's not a length.
That r brings d theta to the edge of the rectangle.
Yeah, d theta is not a length. It's not distance. It's just an amount of openness. So we need length, right? We need length. So that's why I use the arc length formula. R times d theta gives you the right length at any distance away from the origin.
That makes sense.
Yep. So d theta is not length. If it were, it'd be, as you moved away, it would be varying, right? It'd be a varying length. So we need r d theta to get us that length. Okay. So let's go back to this one that we were doing. And we had the region. this was 5. This point was a radical 5, 2 radical 5. This was the line y equals 2x. So now I want to set this up in polar. Okay, so we want to set this up in polar. And so this equals, and again, we're not going to look at these limits and try to figure out what the polar limits are. We're going to use the drawing, right? We're going to use, and this is x squared plus y squared equals 5, 25. We're going to look at the region, and from the drawing, the image of the region, we're going to do the limits, not from the previous limits. So what do we say? It's going to be dr d theta. So r is inside to outside. So we're trying to cover every point in this region. So what range of radii do we need to hit every point in this region? R from what to what?
It would be constant, so 5.
No, we need to hit every point inside the region, right? We
Like
need to
2x.
cover every point inside the region. And R is from inside to out. So look at these lines that I'm drawing. I need to hit every point. So what is R spanning from? From what to what?
From 0 to like SR theta, or like the, I forgot what that equation is.
Right here.
Uh,
But what
oh,
for R, what is R for this?
5.
5, right? It's a circle. Radius 5, centered at the origin. That just means R equals 5. So to get every point in terms of radius, I got to start at what?
At 0.
R equals 0. I got to start at the pole, right? Because I got lots of points down here in my region. I got to cover them, right? All the way to the pole. And I'm going to end at R equals
5.
5. So I want to cover every point from 0 to 5 in radius. I'm trying to get every single point inside the region. And then theta goes from? So my starting theta will be, for this region, is here.
0.
0 to? So you got y equals 2x. What angle is that, right? 2 to 1 ratio. To rise of 2 to a run of 1. So how would I find that angle?
Tangent inverse.
Yeah, tangent inverse, right? So the tangent is 2 over 1. So the angle would be the arctan of 2 over 1, or 2. Then finally, whatever my function is, wherever there's an x, I need for cosine theta. Wherever there's a y, I need r sine theta. Still couldn't make it. And am I done?
And then you need to put like a 5 in there for the radius.
No, not 5.
Oh.
It's every point. We need every point inside here, not just the points on the circle. So the region represents every point from 0 out to 5. So if I put 5, I'm just constricting it to the circle. So I need a
We need an R.
r. Always r. R dr d theta. Then when you're solving the integral, the r, so it comes with the dA, but it multiplies with the f to be your integrand.
For practice, can we just place the R in front of FR cosine theta and R sine theta so we don't forget about it?
If that will help you, I guess, yeah. But there's like, you know, this thing r dr d theta, right? So you say that lots of times, r dr d theta, r dr d theta. So I think it's just as helpful to put it here, because you always, that's just kind of what you say, r dr d theta, r dr d theta. So, but if it's helpful for you to put it somewhere else, as long as it's inside, yep, you can put it there. Okay, does it make sense? So now I want to use this polar integral to get the area of this region. How would I use this polar integral to get the area of the region? What will I do? what will I put here? So it's still, double integrals still find, the polar double integrals still find net volume. They still find difference of volumes, right? There's a whole missing piece to this. There's a surface here in R3 that's hovering over this region, right? So we're just focusing on R2, the plane, to get our limits of integration. But in this grand scheme of this double integral, there's still this surface that's hovering over our region, right? And we're still finding net volume, difference of volumes with the double integral.
Would we set our function equal to 0? Or not 0, 1?
Right, so we're going to set the function equal to 1. So then what will I have in here?
Just r d theta.
Yep. So the function is 1, but we still need the whole dA. So this will give me the area of that thing, because the height of the surface is 1, so the volume that you get is the same as the area of the base, because that's a height of 1. So now when we integrate this, let's do it. Let's integrate. So first step, what am I going to get? I'm going to do the antiderivative of what with respect to r? What am I integrating?
You're integrating r.
R, right? So this is now my integrand with respect to r. I get r squared over 2, and that from 0 to 5. And so then that's 25 halves minus 0 d theta. So then I'm going to get, so now the integral is going to be 25 halves theta, and then evaluated at tan inverse, evaluated at 0, so it'll be 25 halves tan inverse of 2. Area of the region. Questions?
Can you scroll down? Can you scroll down on the page a bit? Like there's a black. Like I can't see what you just wrote.
I'll just write it again up higher. I can't scroll down. I can't scroll down. So you can see this though. So you can finish that integral. It's just 25 halves tan inverse of 2.
Oh, for sure.
So that's the area of that region.
And tangent inverse of 2, would you do that in radians?
It doesn't matter. Wait, no, wait. Yes. So since we're talking about using tangent inverse, yes, this is radians. 2 is a radian measure.
Yeah, so like when you when I would plug that into my calculator,
yeah, you have to have it. You have to have it in radians.
Okay, got it.
Definitely. Okay, other questions?
Where are you getting the r squared over 2 again?
Antiderivative of r.
Oh, okay, I see.
Okay, so let's practice just regions now. So let's look at some regions here, and we're going to practice. Yeah, there it is. This one. So let's practice here. What would our, so again, this is just in the plane. We also know with double integrals, there's a surface that's, hovering over this in the z dimension, right? And we're integrating that surface for the ordered pairs of this region. But just for practice, we're just going to focus on the region and our limits, right? So we want to do r from inside to outside, and then theta 1 to theta 2. So this one here. So what does my r go from? From what to what? And these are all just units.
0 to 2.
He wants 0 to 2. Yeah, so we got to hit every point from 0 to 2. And then theta goes from what to what? So starting theta is 0. What is the final theta?
5 pi over 4.
5 pi over 4. So when you let r change from 0 to 2 and theta change from 0 to pi over 4, you get every point in this region. That's what we want. We want to integrate this function for every point in the region. That means r has to start at 0 and go out to 2. Theta starts at 0 and goes around to 5 pi over 4. And that gets every single point in there. How about this one? R goes from what to what?
Goes from 1 to 2 or 3.
Yeah, so now you think about your archer standing in the origin, right? Your archer stands at the origin and fires arrows straight out from the origin. And the distance away that it pierces in is your lower limit r. And then the distance away that the arrow leaves the region is your upper limit. So 1 to 3. And then from what to what angle?
Pi over 2 over 2 pi.
Pi over 2 to pi. Does it make sense? Okay, let's do this one. So this one's a little bit different. So first of all, r goes from what to what?
3 to 4.
Actually,
Oh, sorry, 2 to 3.
2 to 3.
2 to 3.
And then we got a couple different choices here. Theta goes from what to what?
Negative pi over 4 to 3 pi over 4.
Very good. We could also do, 7 pi over 4 to 8, 9, 10, 11 pi over 4 if you wanted. So you can start all the way over here at 7 pi over 4, 8, 9, 10, 11 pi over 4 would be another way to do that. Okay, questions on the limits, setting up the limits. This would be what, 0 to 2 for r, and then pi to 7 pi over 4 for this one. But then remember, we have some function in R3 that is, we're integrating for the points or over the points of the region. Is the broader context of this, right? This is, double integrals are an R3 phenomenon. They give difference of volumes. Difference of volumes. Any questions on these examples? Setting up the limits for polar double integrals. All right, let's look at another example.
I have a question.
Please.
What's the difference between the dA and the RD theta again?
Nothing.
Okay.
dA equals RD theta. That's what we found. That's for polar coordinates. We found that dA is RD theta. So when you're solving it, you need to write this down, just like we write down dx dy or dy dx for dA. Okay, so here's one. So we want to sketch the region in the xy plane. So I'm actually giving you the integral, and we're going to come up with the region. And we want to change, if we have time, we can change to the other rectangular, but really what we want to focus on is changing to polar. Okay, so here we go. Oh, and so the quiz is just going to be an open quiz that you can just take this weekend. A little bit longer than usual. I think it's like 7 questions or something like this. But you can take your time and review the lecture, review what we talked about before taking the quiz. Take it on just on your own time. So we have 5 more minutes of class here. So what order is this? What order do we have? Or type? What type?
Type 1.
Type 1.
Type 1, which means, what's our mantra? First we go.
We go bottom to top.
Bottom to top.
And then left to right.
Left to right. So what do we have there for our bottom and top? If we have y equals, basically y equals plus or minus for the bottom and the top, plus or minus square root of 16 minus x squared. What do we got?
Circle.
Circle, radius 4. So this is the circle, x squared plus y squared equals 16, which is the circle, radius 4. Okay? And so bottom to top. So the bottom is the lower half of the circle with a minus. Top has the plus. So our bottom is this. Right? Top is the top half. And left to right. So this is 4, 4. So what's the left side of this? The left side is at -4. And the right side is to 0. So if this is the left and this is the right and this is the bottom and this is the top, there's our region. It's the left half disk, right? It's the left half disk of the circle x squared plus y squared equals 16. Does that make sense for finding the region? So here's our R. Okay, so we want to, now we scrap the limits and we set it up in polar coordinates. So you just don't look at those limits anymore. You got the right picture, and now we've had some practice setting up the limits in polar coordinates. What will it be? We want to go, it's going to be dr d theta, right? Dr d theta. So r goes from what to what?
0 to 4.
0 to 4. As theta goes from?
Pi over 2 to 3 pi over 2.
Yep, straight up is pi over 2. Sweeping down to the bottom, 3 pi over 2. Now we have to change, right? We have to change our integrand. So what is x?
X will be r cosine of theta.
R cosine theta. Okay, now we have the square root of x squared plus y squared, which we can plug in r cosine theta and r sine theta and simplify, or you can remember the relationship of r and x and y, right? R is the hypotenuse, x and y are the legs. So what is the square root of x squared plus y squared?
R.
Just r. Here's my dA. So when I change dA, I have to have what?
You have to have another r.
R. dA is r dr d theta. So when I change from dy dx into polar, that dy dx is r dr d theta. So I got my x over r times r dr d theta, and then the r joins up. So in this case, for this function, these r's can simplify because I have an r in the denominator. And so I'm left with 0 to 4, pi over 2 to 3 pi over 2, r cosine theta, dr d theta. Which one would you rather solve? Would you rather solve the given integral, double integral, or the polar double integral?
The polar.
For sure the polar. You got all constant, right? All constant limits plus an easier function. R cosine theta, certainly a lot easier than this one. Although this is doable, U substitution makes, this is not too bad for U substitution, but preferred. But both will give the same value. What? A difference of volumes, right? The volume, difference of volumes of this surface over this half disk. Okay,